Hello again, and welcome to YCP Chemistry Labs, your college's YouTube channel to get you ready for General Chemistry Lab each and every week. We're here tonight right after finishing up the density calculations part 1 experiment, and unusually we have a live studio audience, I guess I would refer to it, here to complete the analysis that's part of density calculations part 2. So briefly, I'm going to take just a minute or two to address the pre-lab questions and the purpose of density calculations part 2, and then we're going to quickly run through the spreadsheet work with an Excel spreadsheet and some example data to show you how simple and easy it is to use an Excel spreadsheet to analyze the data from the density calculations, as opposed to doing it all by hand on your calculator. So the goals of the second part of our density work, which follows up from the, I'm assuming, very brief experiment that you conducted last week in lab, are really threefold in my mind. First, we want to actually use the data from part 1 to calculate the density of rubber. But we did two different data collection sets, if you recall. One was the displaced volume method with the graduated cylinder, and the second was the displaced mass method with the small Erlenmeyer flask. Well, why did we do two? So that we could compare the results, of course, of those two different methods, demonstrating how the choice of our tools and the procedures that we use will have a real impact on the results that we get in an experiment. And then through the analysis of that data, actually, we introduced another variable to our work, which is two different analysis or calculations methods. The simple average method, which many students are probably quite familiar with, when you have several data points of the same value, you simply add them together and divide by the total number of data points. That gives you the average. One of your pre-lab questions has you calculating the simple average, for example, of 3 measured masses, I believe. In the lab, though, today, we're going to learn about how a graph gives us a weighted average for the data that we have for density. And so we want to compare those two to one another. Now, how would we compare them with what we call in chemistry and science in general the percent difference, sometimes called the percent error, but they can really mean the same thing. I think the technical difference would be if you have one value that you know to be true with scientific sort of absolute certainty. Maybe you were measuring the speed of light, so we have the true value for the speed of light. But in a lot of experiments, you might be comparing two different methods. So one method would lead to what you would call the actual or the more realistic value. In our work today, that'll be the graphing value that we get for density versus an experimental value. So you take the difference between those two, of course. Now we take the absolute value of that, because we're always going to quantify error as a positive value. We don't care if we're above or below. We just want to know how far away we are from the true value. So we take the difference between our actual value and our experimental value, and then we would divide by the actual value and multiply it by 100% to get us to a percent difference. So I've mentioned already a simple average, which is part of one of your calculations for the pre-lab. The other calculations focus again on density calculations, which you performed as part of the pre-lab last week. But this time both ask you to put your answer into the standard units for density. So the standard units of density are derived, recall, from the standard units for mass, which are kilogram, and volume, which would be the cubic meter when we think of the linear form of or the measured form of volume, length times width times height. Each of those would have a standard unit of meter. So kilogram per meter cubed. So there's a little bit of unit conversion involved after you do the simple density equals mass divided by volume. So that should be all you need to do to get ready for lab. Today's video, though, is a little bit different. You could use it in lieu of actually going to lab. I'm going to walk you through all the calculations that you would be doing during the laboratory time this week. And so perhaps check with your instructor to be sure, but if you sit down and watch this entire video, you can analyze your data set from density calculations part 1 and then simply quickly hand it in to your instructor and complete the report sheet that accompanies this week's lab. So a really good chance to either have a very short lab when you come to lab next time, or possibly to not come at all, depending on how your specific instructor would like to conduct their lab. It's up to them, not me, just to be clear. So that's it for the pre-lab. Let's get to the data analysis from density calculations part 1. So I have a student assistant who's going to bring up the projector for us while I erase the board here. And we're going to see a spreadsheet that I've created with my data from density calculations part 1. Now, spreadsheets are a really powerful tool. Many students new to college chemistry and math courses might be a little intimidated by the use of spreadsheets, when really we shouldn't be. They are really a time saver. And our exercise here in Gen Chem 1 is designed to comfortably teach us how to use a spreadsheet with a set of calculations that we know we could do by hand very easily. But if you don't train yourself on something easy, you're never going to be able to use a powerful tool like a spreadsheet for something much more difficult down the road. So you gotta work on some of these more simple cases, all right? The power of this spreadsheet comes in its ability to quickly reproduce the same formulaic calculation again and again and again. While you might be able to do 1 or 2 calculations on your calculator faster, when you have to start doing 6, 10, 20 calculations, that's when the spreadsheet's gonna start to win. And so that's what we're going to be showing you. The areas that you can see in yellow on the projector right now are the raw data that you should have from your experiment. Part 1 of the density calculations. Now there were 2 parts of density calculations part 1. The first part, our displaced volume, generated mass of our rubber stoppers. You should have 6 combinations, depending on how you labeled the stoppers, but you had an A, a B, a C, and then an A plus B, A plus C, and B plus C. So you should have 6 mass values, and then 6 accompanying volume values in your graduated cylinder. Okay? Now when we're all said and done, we're going to see the rest of this, how we calculate the stopper's volume, how we calculate the density then, and then how I made this graph and how we're going to use that graph a little bit later on. But I'm going to ask my student assistant to delete all the numbers that we can see right here. And then to just go ahead and click on the graph and delete it for now. All right, so we're ready to begin with our analysis of our rubber stoppers. So if you recall, when we measured the stopper's volume, we had a graduated cylinder that already contained 20 milliliters of water in it. And then when we added the rubber stopper, the volume increased. So these numbers don't represent the volume of the stopper, they represent the total combination right now. And the first thing we need to do is back out or subtract the 20. Again, pretty simple to do on a calculator, but we have to do it 6 times. Still not too hard on a calculator, but what if we had 10 data points or 20 data points? Then it would start to get tiresome. So here's how we quickly write a formula in Excel. You click into the cell, notice that the cell becomes highlighted, and then the formula bar up on the top is where you'll see typing appear. But to start a formula, we always use an equals sign. We don't just type numbers in like we do in our calculator. We would type equals, and I'll go ahead and type it below so that you can see it. Now we want to tell the spreadsheet to take this value, but we don't want to type 24.8. We want whatever is right here. So we just click on that cell, Notice how it put B4. That's the location of this, like we're playing Battleship or something, all right? And then we want to subtract 20 because our starting volume was always 20 for all of these cases. And then when you hit enter, it calculates the volume of the stopper. Now, I admit, in no way was that faster than doing that on a calculator. All right? So for one, there's no way the spreadsheet wins. The way the spreadsheet wins, though, is take the mouse off for a second. You have to pay careful attention to the mouse in Excel. There we go. See how the mouse is changing the box, the square box. Go ahead and click off of the box for 1 second, Luke. Somewhere else. Just click onto a different box, okay? The highlighted box, the bottom corner is always a little square. So click back onto our 4.8. If we grab that corner with the mouse, again, notice how the mouse changed to a crosshairs, and drag it down and let go, it reproduced the same formula. So now, Luke, click into the next cell. It says equals B5. It adapted the formula for the next row down, and then B6, B7, B8. This is where now the spreadsheet becomes quicker than we can be on our calculator. And each time it's subtracting 20 from it. So we quickly have all of our volumes done. All right? And again, the reason we're doing this with a really simple data set is even mentally we can see what these volumes would be by subtracting 20. So we're proving to ourselves that the spreadsheet does this correctly for us. Okay? Sorry about that. The video cut off. Not exactly sure where, but I know we were talking about how when we filled down, that process that we just did was called filling down, okay? Grabbing the square, pulling it down, and it repeats the formula for each row for the new respective values. So now we can use that same approach to calculate the density very quickly in the column that we've set up for our density. So what's our density formula? It's the mass of any given stopper or combination divided by the volume, which we now have stored here in the C column. So we would want to type in the formula equals, again, not the specific value, but where is that value that we want? It's in A4. So you can either click or you could type. So he clicked the first one, but we'll go ahead and type the second one, A4, divided by, so that would be a slash, and then our volumes are in C4. So he would type in C4, and notice as soon as he typed it, how it's highlighting the cell that he picked, or that he typed. So it's very visual, letting you know when you've highlighted a cell. And then when we hit enter, we have a density of 1.3. Now perhaps your numbers aren't coming out with the same number of decimals as mine because I had previously formatted my row, and I'll show you how to do that in just a minute, but let's not get ahead of ourselves. So once again, we've written a formula. It takes a little longer to do it the first time than by hand, but if we grab that corner, pull down, we've got all of our densities calculated once again. Bang. So we've finished those. Okay? Now, let me tell you how we get the nice looking data here. So my numbers are formatted for the right number of significant figures. These are values that show in the volumes uncertainty in the tenths place, so we have to stop in the tenths place. And so the way we would do that is highlight any cells that you are interested in, and then right click while you're in the highlighted area, and choose the Format the Cells option. This is one way to do it. Choose the number, and then you could say how many decimal places. So since I had done this before, it shows 1. You could increase it to 2 or decrease it to 0, but once you set that, you would then click OK. Another option is anytime you have stuff highlighted in the cell, usually things come sort of alive at the top of the screen in terms of options. These buttons up top, yes, increase or decrease the number of decimal places as well. So we would do the same thing with this calculated value. This is more important here because we're taking a number with 4 significant figures, dividing it by a number with 2. The answer should only have 2 sig figs. So we should account for that and be formatting our numbers to show 1 decimal place, since we have 1 number before and then the 1 number after to give us the 2 sig figs. Okay? Now I've already put in a place to calculate the average, the simple average. And again, the way we would calculate a simple average is by adding up these 6 values and dividing by 6. Not too hard, but again, if there were 50 data points, that's a lot of typing on our calculator. Excel is used to doing calculations like this, and it has many pre-built formulas. So if we click into this cell, or any cell where we want to put the average, and we simply start typing, again, equals, because this is a formula, A, V, E, R. As soon as we start typing, a series of options starts popping up. Okay? Let me get my script out of the way here. The first one is average. So if we click on that, all right, we can either click on it and it'll take that. So go ahead and click on that. Yeah. Oh, double click. There we go. Now it changed it to the full word average, and it opened a parentheses. So it wants to know the average of what? So just like in a formula where we selected, take this number minus 20, in a formula like this, we can select all the values we want to average. So you could grab there, all the way down to there, and then you need to end this with a parentheses. Alternately, you could type in the numbers specifically that you wish to average. So we could have typed equals average, open the parentheses, D4 colon to D9. That defines a range, the colon in there. Okay? And when we hit end or enter, again, it's going to calculate the average. It might not show it to the right number of sig figs, all right, depending on how we've formatted, but you can just click that and use your formatting options to produce the same number of sig figs that we have here. Okay? Now, I have the rare opportunity to take any questions. Are there any questions so far, or are we okay with this first set? Okay, we're getting thumbs up from the studio audience. Now, a different way that we could calculate an average is from a graph. And we often like graphs. They're very visual. They show a trend in data. So if we haven't made a graph before, we want to produce a graph of the mass against the volume, where the masses are going to be the y-axis and the volumes are going to be the x-axis. There are several different ways to produce such a graph. Okay? But one such way is to highlight just the just the mass values, including the header that I put in here. So from A3 down to A9, and then go to the insert menu at the top. Over here we have a bunch of different charts. We can make many different graphs. What we want is what's called the scatter graph. Okay? And it has a little drop down menu because there are multiple varieties of scatter graphs. While these ones might be tempting, that looks like they have lines on them, and maybe you've seen graphs with a line, those are connect the dot lines. They are not the line we're looking for. We want the first option right there. So if we click on it, it's going to put a graph up there that is not quite what we want just yet. So now, we'll notice we can be in the graph or we can be out in the spreadsheet. When we're in the graph, you will notice the highlighting around the graph. Okay? If we click out real quickly, the corners are no longer sort of big. So when you click back into the graph anywhere, you see it sort of highlighted double line, and you can change the size. Okay? This doesn't look like much of a graph or a trend so far, because right now our mass values are plotted against a generic 1, 2, 3, 4, 5, 6. This is simply mass 1, 2, 3, mass 4, 5, and 6. There's no correlation to our volume yet. What we need is to get our data in there. And so once we have our graph selected, right up here there's a button that says select your data. Again, there are other ways you can do that. You can format the data. So it brings up this little window about selecting the data. What we want to do is make sure we have mass highlighted, and then we want to edit that data set because it's incomplete. Okay? Now, the mass are the y values, so this is correct. This box right here is going to let us do three things. Say what are our y values, okay? What are our x values, and then what's the name of this data. So let's change the name of this, okay? Right now it's just taking that cell right there. You can just highlight all that and delete it, and we can call it density part 1 or displaced volume method. Something to make it distinct, all right? Now, how do we get our x values? To get the x values, you want to click this little button, which is going to then, it looks like it's going to shoot you out of this box back into the spreadsheet, and then you can highlight all of the data for volume, which is what we want. Okay. Now we actually want to highlight the title in as well. Okay. I think you're going to need to delete all of that. You just sort of double did it. Just go ahead and delete all of it. And then start with the stopper volume down to the last stopper value. And then hit the little red arrow. You're ready to deposit that. Okay? I guess I was wrong on that because we don't want the stopper value because the y value started with 4. So you want to drag it from C4, down to C9. There we go. As soon as you hit OK, bang, you see how our graph was updated? Now we see what looks like much more of a straight line we've got there. Okay? Quick question.
Can you show how to do that again?
Okay, show how to do that again. So let's hit the undo button a couple times so that the graph goes back. Doesn't look like any kind of a trend. Click on the graph. We can see that it's active for graph mode. And the other thing is the menus change up top. Select the data that you want to use for your graph. Now you already have half of a data set in there. So what you want to do is edit the data set that you already have. You could actually start with a totally blank graph. Okay? We renamed the series Displaced Volume Method or Density Part 1, something. We renamed it. Okay? Otherwise it's always just going to be a generic, the first cell that you just clicked in. Okay? Now, to get the x values, we used the little select the range button and highlighted in the table the values that we want, and then the down arrow, red arrow, puts them back in. And no sooner do you do that than you automatically saw the chart update itself, the graph update itself. You click OK, OK. And you have a formatted graph now. Okay? Now the graph looks nice. There's a lot of work to do with this graph though. There are no labels on this graph right now. Okay? So there are no labels on this graph, which are a crucial part of having a properly built and formatted graph. So to get labels, there are a couple of different ways to do it. But one of the nice features of the current version of Excel is up here in the quick layouts. If you use the drop down button on the quick layouts, it gives you an idea of what stuff it will let you feature. This first option, don't click it just yet, has a title, a y-axis label, an x-axis label, and it has a little key for what the data is. So let's just click that one. It's pretty simple. And it changed our graph. Generically added axis titles. Okay? It kept the title we had put in there for the overall graph. Now we don't need this because there's only one data on here. So you can click it, make sure that you only selected it, and then you can delete it just with the delete key on the keyboard. To change the axis labels, you double click into them And you can highlight all that and type in what they really are. So our x-axis is our volume. And a properly labeled axis would have not only what it is, but also the units in parentheses after it. Okay? Same thing with the y. I know it's at sideways, but you can type, and you'll see it's going to type up above where it's lets you type sideways. Okay? Stop or mess. There we go. All right. Now we probably don't need these lines either in this case. Sometimes we might have vertical lines and horizontal lines. So if you carefully click on one of the grid lines, notice that they've now been selected. Anything that gets selected, it highlights it with little dots for you. And you can just delete them just like you did with the key. All right. And this is my preference. Graphing preferences are really across the board. But for just a simple scatter graph, I don't like all the extra bells and whistles getting in the way of showing the data. And so I like to clean out a lot of that. And I would encourage you to start with something simple like that. Okay? Now, this graph plots mass over volume. The slope of any line, you may recall from grade school or algebra, is the change in the y-axis value divided by the change in the x-axis value. So for this graph, that would be something about the change in mass divided by the change in volume as we move from one point to the next. Mass divided by volume is density. The slope of this graph is the density of our rubber stoppers as well. All right, a different way of calculating that density. All right, and this would be a weighted average because it's going to use a graphical method. It's actually a linear algebra technique called linear regression that finds the best fitting line through those data points. Okay, and it devalues points that are far away from the data sets and more heavily values data points that are close, in short. How do we get that? In the graph, we click on one of the data points, make sure that they highlight. Notice also that it highlights the data that's in your graph. Now there are, again, a few different ways to access this, but the quickest is to right-click. The right mouse button, at least when you're working in Windows-based machines, not quite as sure if you're working on a Mac, but the right mouse button, it has a lot of options on it for you. All right? And the option that we want to choose right now is to add a trend line. It brings up a series of options. What kind of line? Not all lines are straight. All right? Sometimes you have curves, but this time we do want the linear option. And Excel will show us the equation of our line and how good that equation, how well I should say, it fits the data. This is what's called the chi-squared or r-squared parameter. The closer that number is to 1, the better all your data fits on that line. So I have a pretty good data set here as my example set with the 3 nines, 0.998. But here's the slope, right? Because all lines are y equals mx plus b. So the slope is this 1.2456. And you see that the 1.2, if we take just the first two numbers as the sig fig, matches our density that we calculated with the simple average. Okay? Now we're going to do this again with our displaced mass method, and then we'll be able to use more of those significant figures. We can't really use them right now because we're limited to 2 sig figs from our data set. All right? I'm going to take a quick pause right now, and then I'll get the screen set up for the next part of the experiment. Yep. Okay, now we're ready to try and analyze the second set of data from the displaced mass method. This is just a touch more involved, and conceptually we need to figure out 1 or 2 steps in this process. But again, with a spreadsheet, it's going to be quicker to do it this way. We're going to need 5 columns this time instead of the 4 that we generated for the first part. we're starting with mass of our stoppers, which we should be able to copy and paste from the first set, to be honest. And then you have your 6 accompanying masses that were for the combination of the flask filled with water and your rubber stopper in it. And we have one other value, which I've stored down here below my data set. You could put it wherever you'd like, sort of out of the way, which was the flask filled completely with water and its glass stopper in it. And we're going to need that value. This is sort of like the 20 milliliters that we subtracted in the first part of the experiment. Okay? And so that's how we're going to use that. And I'm going to show you a special way to use that. So, to get the mass displaced, our experiment is really a conservation of mass. It's like a seesaw. This picture is described in the lab manual. Before we had, this is sort of our before set. You have a rubber stopper or combination, and then you have a flask filled with water. This. There's some total mass here. And then somehow, when you put the stopper inside the flask, it has a mass that's different from if you just added these two together. Notice that? If we put this mass inside here, it's not the same as when we weighed it that way. That's because some water splashed out. That's the mass that we would like to know. So this is a seesaw. These two sides are equal, right? So how can we write a formula that would let us calculate this value? So in our cell here, we would want to start with an equal sign. Well, we want to add together the mass of our stopper. Where's that? Click the cell where the stopper mass is. We want to add to it. Now we want to add to it this value. Every single time, this value. If we click this value and then we use the fill down feature that we did earlier, it's going to also try to fill this down. So we need to use a special version here where if we put a $ in front of the cell parts, in this case A27, that is special syntax or language in Excel that says always use this cell, A27, okay? Don't fill this one down like the other cells. Always use this cell for this specific thing. Alternatively, you could type in plus 113.274, your mass. But the beauty of this is if I change this number into a different experiment, all I have to do is type the new number in here and it automatically updates in the formula because we're referencing it in a cell. Okay? So that's this side of our seesaw. And then we want to subtract then the flask, water, and stopper. So minus then the B column. All right? And when we hit enter, that should give us the mass of water that is displaced in this experiment. All right? And again, you can then fill this down and you're going to quickly reproduce that calculation for each of your masses. Now let's click into one of these again and we'll show that it's referencing A18 plus this cell still, okay? And then minus the B18 cell. So you see that $ keeps this cell anchored while the other ones are allowed to fill down with them. Okay? So now this gives us the mass of water displaced. But what we need is the volume of water displaced because that's the volume of the rubber stopper. Just like in the last experiment, the volume went up when we put the stopper into the graduated cylinder. Well, now the volume went up and that water splashed out of the flask. So we're going to make use of the density. Now the density formula, right, is mass divided by volume. So the volume displaced would be the mass displaced divided by the density of water. So what's the density of our water? Okay. I have a internet window open as another one of the tabs on the machine right now, open to a website that quickly lets me calculate the density of water. Go ahead and pull that up. This is available through our YCP Chemistry lab site maintained by Dr. Forsman. But this is a really nice, there are many sites like this, but you want to go to a reliable, reputable site. And all you have to do is type in your temperature. Let's say that the temperature was, I don't seem to have it recorded in my notes, but let's say the temperature was 21.2 degrees Celsius. 21.2 degrees Celsius. And as soon as you hit enter, did you hit the enter key?
Yeah.
Okay. It brings up the density for you in grams per centimeter cubed or grams per milliliter. So it's saying 0.99795, it looks like. That's several more sig figs than we probably need. Let me take one more. It's going to be a 2. All right. So now we come back to our Excel spreadsheet after we find the density for our specific temperature. Everybody has to do it for their specific temperature. Okay? All right? So we can then type in that value specifically. So our formula here becomes equals, take the mass, we have that in our cell C, divided by this, in my case, this density value, 0.997952. Notice it's about 1 because the density of water is usually about 1, a little bit less as it gets warmer. When we hit enter, that's the volume, and then we can fill that down. Now, unlike my first set of data, where the numbers were all nicely formatted, these haven't yet been formatted. So let's think about how many sig figs this should have. Our masses had originally 4 significant figures, but specifically to the thousandth decimal place. So the displaced mass can continue to go to the thousandth decimal place. And that means all of these values have 4 sig figs. So we should probably format these so that they end in the thousandth place. And that would give all of them 4 significant figures as well. So Luke's going to use the decrease the decimals. And there they go. They just disappear until we're right there. So now we've got some properly formatted numbers there. It's sort of the cleanup that you can do at any point. You don't necessarily have to do that right now. Okay? So let's get an average. Remember how we did that last time? We click into the cell where we want to calculate it. All right. Oh, I'm sorry. Sorry. I got ahead of myself. That is simply the displaced volume. Next, we need to calculate the density now. So we now need to take the mass of the rubber stopper divided by its volume. Oh, that's the wrong mass, Luke. That's the displaced mass of water. We want the mass of the rubber over here in A divided by the volume, which is now in D for us. Okay? The displaced volume of water equals the volume of the rubber. So they are the same, and that's why we're dividing by that value here. Now these should come out fairly similar to what we had in part 1 because it's the same rubber stoppers. Okay? All right? We can fill that down and reformat how many sig figs? Well, both of these have 4 sig figs in them, so we should go to the 3 decimal places because we have 1 digit out front. Okay. So part 1 of the experiment, we ended up with densities like 1.2, 1.3. But now, because we've used only mass and our electronic balance gives us more significant figures, we have 4 significant figures. So a much more accurate way of calculating the density of the rubber stoppers. Okay? Now, the rest of our work is pretty much the same skills that we've done already. we can now build another graph. Remember to do that. We'll just do it real quickly. I'm sorry if it's going quickly for you, but you'll be able to take your time when you try it on your own. To do the graph, we highlighted first the mass values. We inserted a scatter plot with no lines or anything. Then we selected the data. We want to edit the set that's there, rename the chart. This is now part 2, or displaced mass method. Select your X values using the little button with the arrow that goes out to the spreadsheet and then comes back into it. So you go out and you select your displaced volume values, just the numbers. And then your graph updates once again. From here we change the layout using the quick layout button so that we can have titles and labels. Don't worry about updating the labels right now. And then we added the trend line. Right-clicking on the data, add that linear trend line. Okay, so we added that trend line, and again, we can do all the cleanup work from here on out. We didn't calculate our simple average. We can do that in the cell underneath the density columns the same way we did in the first part of the experiment. Equals, start typing the average or the whole word average. Okay, it's going to say, well, what cells do you want? So you just highlight those. Okay, end it with the parentheses, and then you've got it correctly calculated there. So here's what we want to compare. What we're saying moving forward in science for you. When you calculate, if you can, a slope, this is the density, but the number coming off the slope is considered more accurate for us because it weights or de-weights any point that is far away from the line. So some of you might be looking at your data sets and seeing erratic data points. Those numbers are being not completely thrown out, but they're being devalued in the analysis. So we have more confidence in the number coming off of the graph than we do from the simple average right here. Okay? So at this point, we've really walked through all the calculations. So for your lab report for density part 2, you need to print out 2 pages, essentially format your paper so that you get a page for the part 1 displaced volume method with its graph, and a page, or the back of that page if you want, for the part 2 method, displaced mass method. So it should show all of this with your correct formatting, titling and everything, and your numbers. Okay? And then there is a report sheet available in the Fact Data Drive, my Fact Data Drive, W. Steele, that has several questions for you to answer, asking you to reflect on the different methods and which the slope versus the simple average, volume versus mass method, for example, asking us to think about the design of this experiment and which number we have the most confidence in. All right, and you put all that together, and that's your lab report for density calculations part 2. So thanks for hanging in there. Feel free to ask questions during the lab time if you've been there, or follow up with your instructor. And I hope you've had a good experience and learned that you can use the spreadsheet to accomplish a lot of calculations, perhaps more quickly and accurately than you could by hand. Have a great day.